just going to put it on record. Does that make sense, guys?
Yes.
Cool.
Yes.
There's one other way that you can have asymmetry in a molecule besides lone pairs, okay? So what we've been considering so far is a molecule that has all of the same attached atoms around the central atom. So for example, if I had carbon tetrachloride, carbon tetrachloride has carbon in the center and all of the chlorines around the outside. I'm doing this kind of quick and dirty, so if this is a little fast for you, that's okay. I just want to make sure that everybody understands symmetry versus asymmetry. So in this molecule, carbon and chlorine definitely have a polar bond, right? Is everybody okay with that?
Carbon and chlorine polar bond. Because the chlorine has a higher electronegativity?
That's exactly right, yes. Because okay. Carbon has a higher electronegativity.
Gotcha.
The carbon-chlorine bond is electronegative. The chlorine is more electronegative than the carbon. So what we can do is we can draw a dipole, right? And that's one of the things you're going to do in lab this week. So a dipole has this positive end, indicating that this guy is partially positive, and the arrow direction indicates that this is partially negative, right? But we also have another dipole pointing this way, right? And these two dipoles cancel each other out. Is everybody picking up what I'm laying down?
Yeah.
So the same would be true for the top and bottom chlorines, right? And that's why this is symmetric, which means it's non-polar. Does that make sense, guys?
Yes.
So the dipoles going in the opposite direction just means that there's no net charge?
Correct, exactly.
It cancel out?
Exactly. So you can have polar bonds without necessarily having a polar molecule. Can I turn the page, guys?
Yes. Well, for me.
Anybody need me to wait?
No.
Okay.
No, thank you.
Okay, so the other way that we could have asymmetry in a molecule is if we had different attached atoms. So let's say we have carbon, 3 chlorides, and 1 hydrogen, right? So now this molecule, and if you didn't know how to draw this molecule just by looking at that chemical formula, that's okay. Again, I've done this a lot of times, so I kind of know what all of these look like, but it's okay if you didn't, right? So do you see how this has the same shape and the same molecular geometry as the previous one, right? What is that geometry?
Linear. Does it have lone pairs?
Has 4 attached atoms.
Oh. Tetrahedral.
Tetrahedral. Does everybody see that?
The bottom one?
Yeah, because there's 1, 2, 3, 4 attached atoms, right?
Mm-hmm.
So this is tetrahedral. Does that make sense, guys?
because the top ones are attached. That's what you said.
All of the atoms are attached.
Well, yeah, but can you just explain that one more time? I'm kind of confused.
So if you have 4 attached atoms, right? 4. Steric number basically means attachments.
Okay.
But 4 attached atoms around your central atom means that you're tetrahedral.
Oh, okay. I see it now.
Right?
Okay.
So, okay. So everybody with me?
Yeah.
Okay. So in the previous molecule, we had all chlorines, right? In this one, we now have a hydrogen here. So there's the net dipoles, or there's dipoles in the same place that we drew them before. And these guys cancel out, right? But now carbon and hydrogen, is that a polar bond?
No, not polar.
No, that's nonpolar, right? So you're gonna have a dipole, right? That looks like this, and there's nothing to cancel it underneath, right? So this is a polar molecule, right? Because not all, of the attached atoms are the same. Does that make sense, guys? So just a reminder, in our previous molecule, right, we had 4 chlorides attached, right? All the same atom. Now here, we don't have all the same atoms, right? So when you don't have all the same atoms around the central atom, then you create asymmetry. Does that make sense, guys?
Yes.
Cool.
Thank you.
All right, so I'm going to keep using this molecule, but I'm going to simplify it and take out some of the arrows because they're a little confusing that way. So if we have this guy, right? The way that we indicate that there's a partial negative is by doing this little delta negative, and we put a little delta positive next to the carbon to indicate that there's a partial positive there. Does that make sense?
Can you repeat that last part?
Yeah. So this delta negative indicates that there's a partial negative on this part of the molecule, and this delta positive indicates that there's a partial positive on this part of the molecule. Does that make sense? So basically what we're saying is because chlorine likes electrons more, meaning it's more electronegative, right? It's going to pull more of the electrons toward itself, right? By pulling more of the electrons toward itself, it's taking away some of carbon's electrons, right? Leaving carbon with a slight electron deficit. So electron deficit gives you this partial positive. Extra electrons gives you this delta negative. Does that make sense, guys?
Mm-hmm. Yeah.
You don't really need to write the positive on every atom, just...
No, you don't necessarily need to write it on every atom, because what we're saying here is these chlorines are probably pulling relatively equally, right? So I think, let me see, what molecule is this? So there's some pictures from the lab manual that show it maybe a little bit cuter than I'm drawing it. So this is a water molecule, right? Oxygen is more electronegative than hydrogen, right? So you have this partial negative on oxygen and a partial positive on hydrogen. Is that your kid, Zainab?
Yeah.
No, it's okay. I'm so lucky. My partner and I have been able to figure out a schedule. So he's doing like Elsie preschool right now. So
we have a four computer now working. Like each one has a class.
Oh, neat.
Like, oh gosh, it's kind of tiny place.
Yeah. It's exciting.
Excuse me, Professor, can you talk a little about intramolecular force a little bit?
Yeah, so that's what I was going to get to next. So now that we kind of understand how we can get polarity in a molecule, right? Now we can talk about the consequences of that polarity in a molecule, right? So if we have these partial negative and partial positives on water, I kind of want to make that closer for you guys, right? So you can see, sorry, I'm holding this up with my hand, that's why it's moving. You can see the partially negative part of the water molecule, that partial negative on oxygen, is going to be attracted to the partial positive on the hydrogen, right? That is called a hydrogen bond. It's technically a dipole-dipole bond, but it's the strongest kind of dipole bond, right? And the reason being is because hydrogen only has one electron. You guys remember that?
Yeah.
Some dusty place in your brain?
What page is that on?
That hydrogen has one electron? Or you mean the lab manual? 76.
Yeah. Sorry. Thank you.
No worries. So if hydrogen only has one electron, right, and oxygen is really hungry for electrons, then oxygen is going to be basically taking away hydrogen's only electron, right? So this makes a really, really strong partial positive on the hydrogen and a really, really strong partial negative on the oxygen, right? The strength of this dipole is why hydrogen bonds are so strong, because these are very polar bonds. And there's some other drawings of the dipoles on oxygen. Dipoles are the same idea, but they're a less strong interaction, right? They still have partial positive and partial negatives, but now they're a little bit less strong than hydrogen bonds.
Is that the negative side attracted to the positive side?
Yes. So when you have a net dipole, we have a polar molecule, right? So you see this is the net dipole that's on water, right? Making the hydrogens partially positive and the oxygen partially negative, right? And that's what gives rise to these dipole interactions. But in the case of water, it's so strong that we have a special name for it, right? Which is hydrogen bonds.
And you only find that when there's hydrogen bonded to oxygen, nitrogen, or fluorine. These guys aren't bonded to each other, by the way. I'm sorry. I'm drawing this lazily. I've got this guy or this guy. Sorry. My poor lab manual. Guys, give me 1 sec. I'm going to plug in my phone because I'm very confident that it's going to die soon.